So I have a little bit of bad news. This video is going to be a bit more challenging, so I would highly suggest taking a bit more time with this, maybe watching it twice or stopping it occasionally to make sure you understand all the steps that we take. These are things that we are going to use later on, so it's not something you can just be like, oh, that was hard and now I'm going to forget it. Do your best to try to grasp what's going on in this video. Alright, let's get to it. So in the previous video we saw that the electric field due to a single point charge is kq over r squared, or we could write this in terms of other constants, 1 over 4 pi epsilon naught q over r squared. And that works fine as long as you only have a few charges to deal with. But if we have a whole bunch of charges, what we call a charge distribution, then we need to use a bit of calculus to add up the contributions from all of those charges. So the first example we're going to look at is a ring, and if we imagine like a metal ring and there's charge distributed all throughout that ring, then each segment of this ring, we're going to divide it up into little chunks, is going to contribute a little bit of E field, dE, according to the little bit of charge on that segment. And then to get the total electric field, we're just going to add up all of those infinitesimal contributions from the infinitesimal chunks of charge, and that will allow us to find the electric field. Now this is a vector quantity, so at times it will be useful to break it up into components, and then you can find each component separately by doing its own integral for the component. Alright, let's get to it. Here is a nicer drawing with a nicer looking ring of radius A. We are concerned with the electric field at a point P, which lies along the axis running through the center of the ring. This is going to be quite a bit simpler than some point off axis here, because we're going to have a bit of symmetry. We can already see, if I am considering this little chunk of the ring here that has a certain amount of charge on it. Now if I say the total charge on the ring is Q is the total charge, then this little chunk here is going to have a little bit of that Q that I'm going to call dQ for now. So that little bit of charge is contributing an electric field, or a part of the total electric field, in this direction, which we can break up into vertical and horizontal components. But if I consider another infinitesimal chunk on the exact opposite side of the ring, that will contribute an electric field going this way, which will also have vertical and horizontal components, and these vertical components will cancel out. And that argument can be made for any pair of points on opposite sides of the ring. So all these vertical components and the z components also will cancel out, and all that you will be left with are the x components. So we can say that the total electric field is actually just the x component of the electric field, and to find the x component we just need to sum up all of the infinitesimal x components, and we can do that by doing the total E field times cosine theta, because that's going to give us our x component from the total E field. Now dE is defined as k dq over r squared, and so we can substitute that in, and so we've got we can pull the k out front because it's constant, and we're going to have integral dq over r squared times cosine theta. Okay, and in fact r is constant as well, so we could pull that out if we like. We'll do that in the next step. But we do need to relate dq to cosine theta. So dq is the amount of charge on that little infinitesimal section. So in order, we can figure out how much charge is there if the total charge is q by taking the total charge and dividing it by the circumference, which is going to be 2 pi a. So this quantity here is the charge per unit length, and then if I multiply that by the length of this little segment, dl, then that is going to give me the amount of charge on that little segment. And often we will rewrite this charge per unit length here as a sigma, which is the linear charge density, and we just don't have to write as many symbols when we're carrying out our integral when we do that. So I'm going to go ahead and make that substitution here. So my electric field equals k. I'm going to have the r squared here, and then instead of dq I'm going to have lambda. Now lambda is constant, so I can pull that out here as well. So I'm going to have cosine theta dl. And in fact, cosine of theta is constant because as we go around this ring, theta is always the same. So I guess I should have written that over here. That's an ugly integral. Okay, and the limits of integration, if we start at one point and go around, is from 0 to 2 pi a. So this is a nice easy integral. We're summing up each segment, so it should give us the total length around the ring. So it's just going to give us 2 pi a. So we've got k lambda r squared cosine theta times 2 pi a. And now we just need to substitute some things in and simplify a bit, and we are almost home free. So we can go ahead and substitute back in for lambda. I guess it didn't save us a whole lot, but that's going to be q over 2 pi a is our lambda. Then we've got our k over r squared cosine theta, and then our 2 pi a on the end there, and you probably noticed those go away. Now we're going to write this cosine theta in terms of x and r. So cosine theta is x over r. So if we substitute that in, we get qk over, times x over r cubed. And again, we're almost there. Now, this is, a valid expression, but we're interested in any point P that could be really at any location. And so we want to write that in terms of x, and so we can see how the E field changes as a function of x rather than as x and r. And as we can see here, r is the hypotenuse, so r squared is going to be a squared plus x squared. So if we make that substitution in here, then we're going to get kqx all over x squared plus a squared, the order doesn't matter, to the 3/2 power. And there we've got the electric field along the axis going through the hoop as a function of x. And we like to do, whenever we get a solution like this, we want to check the extreme cases and see if it makes sense. So for instance, the electric field at x equals 0, we would expect at the middle of this ring that all of the electric fields from each infinitesimal segment would be pointing in and canceling each other out. And we go ahead and plug in a 0 there, and we would get 0. And then we also want to look when x is much, much greater than a. So when we get really far from this hoop, then really the fact that it's a hoop kind of goes away, and it's just the same as having a point charge there. And so this should reduce to kq over r squared. And so if x is much larger than a, then this really doesn't matter, right? So you'll have kqx over x squared to the 3/2 power, because the x squared part will dwarf out the a squared part. Okay, and so these guys go away, and so you have x cubed down here, which cancels with one of those, and yes, you end up with kq or qk, whichever way, over x squared. Did I screw that up? Yeah, that cubed should have left a squared. Ugly cancellation, but anyway, it works out. All right, on to the next one. Here we have a very long line, a very long wire that is charged. So long we could even say it's an infinite wire. And again, we want to find the electric field at some point P here off some distance x from this wire. So again, we can write, we can think about the x and y components. By the similar logic, there's another segment down here that's going to have an electric field over there, which you can break up into vertical and horizontal parts. So again, the y components are going to go away, and we're just going to be dealing with x components. So we can just go ahead and say this is the sum of all the x components is going to give us our total electric field, which again is going to be dE cosine theta. All right, now if we're looking at the charge on this little segment here, Since it's an infinite wire, you don't really want to say total charge Q divided by infinite length, because I guess you'd have an infinite amount of charge if you're going to charge an infinite wire. But we can still just say that the amount of charge on each little segment is the charge per unit length, lambda, whatever that happens to be, times the width of this thing. And since it's vertical, we're going to go ahead and call that dy this time. So dE is k dq over r squared, and then we can make that substitution. So my E here is going to be we'll go ahead and pull the k out, integral of, I'll pull the lambda out as well. So I've got my cosine there, and then I've got my r squared here, and then I've got dy. So at this point, it's a little trickier than the previous example because theta is not constant. It's changing as we go up and down our pole here, summing up our little infinitesimal segments. And r is not constant either. That's also changing. So we need to rewrite these quantities such that we have either all thetas or all y's, and everything else in there has to be constant. So there's a couple of different ways we can do this, and I'll show you each. But you might just want to start out by playing with some different trigonometric relations and see what you might be able to substitute in to make this integral work. So for instance, we know that tangent of theta is y over x, and so y equals x tangent of theta. And here we've got a dy, so we might be interested in taking the derivative of this guy, and we'll get dy. The derivative of tangent is secant squared, or to keep it in more common trigonometric terms, we'll say it's 1 over cosine squared. And then due to chain rule, you need to have d theta. So now we could substitute this in. X is constant, so that's nice. One of these cosines is going to cancel out, and then we've got a d theta here. We've still got that r to deal with. So let's look at what else we can do. We've got that cosine there, and we know that cosine theta is x over r. And let's see, we've got an r squared down here, so we could solve this guy for r squared. Well, r is going to be x over cosine. And then if we square everything, then we've got something we can substitute in there. So now let's go ahead and make these substitutions and see where we're at. We're going to have k times lambda times the integral. I'm going to leave that cosine theta up there for now. And then this r squared is going to be x squared, and I'm going to get another cosine squared. So I can just make this cosine cubed, and then I can plug in my dy here, which is going to be an x cosine squared theta d theta. Try not to get things too confusing here. And we can cancel this out, and we're just left with a cosine there. We can cancel that out, and x, as I mentioned earlier, is constant, so we can go ahead and pull that out, and this turns out quite nice. Sorry, the x is in the denominator. Go away. We just have the integral of cosine theta d theta, which is nice and easy. Now the limits of our integration, if we're assuming this is an infinite wire, or if it's not infinite, we can just assume that it's very long. So we want the limits of our integration to be from negative pi over 2 to pi over 2, essentially negative 90 degrees to 90 degrees. So we can go ahead and perform our integration here, and we're going to have all the constant stuff out here. Integral of cosine is going to be sine theta, and then we're going to evaluate from from negative pi over 2 to 2. And sine of pi over 2 is going to be 1. Minus sine of negative pi over 2 is a negative 1, so this makes it a positive, and we end up with 2k lambda over x, which is all well and good. We could also rewrite this if we wanted in terms of epsilon naught, in which case we'd have, we'd have 1 over 2 pi epsilon naught, because we canceled that 2 up there, times lambda over x. So just another way of writing it. Now, you might say all of this stuff was a bit confusing and a bit harder. Why didn't we just substitute in for cosine theta and r squared here? And we could do that just fine. I will show you that real quick. So you'll still have the k times lambda out front. Cosine theta we said is x over r. So you've got x over r cubed dy. And then you can substitute in for r, because we know r is square root of x squared plus y squared. So you're going to have k lambda times the integral of x over x squared plus y squared to the 3/2 power. And then just take the integral with respect to y. So this is probably a bit more straightforward substitution. You end up with an uglier integral, but those of you who can do this on your calculator, it's not a big deal. You do end up with the same solution in the end. Alright, one more example. Here we have a flat disk that is charged, has a total charge Q on it, and we want to know the electric field at a point P above the disk. Now, what we're going to do is divide this disk up into a bunch of rings, and we already have an expression for the electric field due to a ring. Now I'm going to call it dE instead of E because we have a bunch of rings. So this is from one of the rings, and then we're going to sum up over these. And I'm going to write it in terms of 4 pi epsilon naught. And before we did this in terms of x, but now that we're going in this direction, and they call it the z-axis in this diagram, we're going to go ahead and call that z. So z squared plus r squared, because r was the radius before we had an a there, right? That was the radius of our ring, to the 3/2 power times dq. And now dq is going to be the charge per unit area times the area of the ring. So the total charge is q, and then if we divide that by the area, that's pi big R squared. Okay, so little r is the radius of each ring, and it's changing, and then big R is the total radius of the big disk. Okay, so that is our charge per unit area, and then we need to multiply that by the area of the ring, and you might think you'd do pi r2 squared minus pi r1 squared or something like that. But since we have an infinitesimal width here, what we're going to do is we're going to say the area of that ring is the circumference of each ring, 2 pi r, times the infinitesimal width of the ring, dr. And we're going to go ahead and write this q over pi r squared thing as sigma. So we use lambda for charge per unit length, and we use sigma for charge per unit area. And then we've got 2 pi r dr. So this is our dq here. So to find the total electric field, once again, we sum up all of this, which is going to give us, if we start, well, we'll go ahead and, we'll pull out the constant things. So we've got z out here that we can pull out over 4 pi epsilon naught times the integral from 0 to big R, because I'm going to go ahead and substitute this in for dq. So I'm going to have a sigma, which I can pull out because that's constant, and then I've got a 2 pi r. I'll put the 2 pi out here for now, and then I've got r dr left over from this guy, and I still have the z squared plus r squared to the 3/2 power. Now z is constant because we're just considering it at that one point, so we can go ahead and evaluate this integral now. Not the prettiest integral ever. You can look it up on an integral table in the back of your book, use Wolfram Alpha, use your calculator, or do a u substitution or something along those lines if you really like. Alright, so let's cancel out some of this stuff. That goes away, this cancels there, and becomes a 2, and so we've got z sigma over 2 epsilon naught, and then we've got this integral here, which works out to be 1 over z squared plus r squared to the 1/2 power, negative sign here, and this whole thing is evaluated from 0 to r. So if you plug in r, you're going to get, we'll go ahead and do the full thing. So you're going to have negative 1 over z squared plus big R squared to the 1/2 power minus, now you're going to plug in 0 here. So you're going to get 1 over z squared to the 1/2 power is just going to be a z. But then we're subtracting it, so that actually gives us another negative sign there. Now if I distribute this z through, just go ahead and cross it out there and put it here and here, this term is going to be 1, and so we end up with sigma over 2 epsilon naught times 1 minus z over z squared plus big R squared square root the whole thing. So there is our nice big ugly solution to this problem. And in fact, we're not going to use this formula very often at all, but we're going to use an approximation that we get from this. And if we say that r is much, much larger than z, those are greater than signs, in that case, and this can happen either if you have a very large disk, a lot of times we'll consider our plates to be infinite in size, in which case this is definitely true, or we can just say that we're really close to our plate, that z is very small. So if that's the case, then this term here, this z squared becomes insignificant because the r squared is much larger. So you end up with this term being z over r because you had r squared square rooted. And again, r is much larger than z, so this thing approaches 0. So you end up with just this term. So in the case that r is much, much larger than z, you get an electric field that is just equal to sigma over 2 epsilon naught. And this is a very important solution that we're going to use quite a bit. So let's look at an application of this little approximation here. If we have two charged plates and we assume that these plates are infinite plates, very large, or that d is very small, even though the drawing doesn't look that way, in that case the electric field is actually constant, right? It was sigma over 2 epsilon naught, so it doesn't change with distance. So over here, due to the positive electric plate, charged plate, you're going to have electric fields going out, and they will be the same magnitude at any distance. And here for the negative plate, you're going to have electric fields going in, and they're the same magnitude at any distance. So outside of the plates, you'll end up with electric fields in opposite directions, and we assume that the charge on both of these plates are of equal magnitude, so these electric fields are of equal magnitude. So these guys are going to sum to 0 out here, these guys are going to sum to 0 out here. Here you just get multiplied by 2, so you get an electric field of sigma over epsilon naught. And as ugly as all of this video was, and it's important to be able to follow along to some extent, there's also some interesting results. So we had the electric field due to a point charge. I'll just say PC for a point charge. That was KQ over R squared. And then we had the electric field due to a line of charge, we'll say LOC. That one was 2 K lambda over R. And then the last one, which was due to a plate or a plane of charge, was, as I just mentioned, sigma over 2 epsilon naught. And what's really interesting about this is here we have an inverse square relationship. Here we just have an inverse relationship with distance. And here we have no relationship at all with distance. So as we increase the dimensions of our charge distributions, we decrease the dependence on distance. Very important, wonderful things. Okay, we'll see you next time.